14,000 miles of continuous steel wire shape the Brooklyn Bridge, a length sufficient to wrap halfway around the planet. To comprehend this century-old titan, we must decode the hidden physics behind its creation. A primary structural cable measures no thicker than a human arm, yet this slender profile defies colossal physical forces. Hurricane winds batter the suspended span. Thousands of tons of moving vehicles strain the deck every hour. The paradox is absolute. Visually fragile, structurally invincible. The phenomenal resilience of such megastructures depends entirely on the hidden structural properties locked deep inside the metal itself. How exactly does brittle mountain rock transform into an indestructible engineering masterpiece? The answer requires tracing the raw iron back to its brutal genesis, stepping directly into the pure, incinerating. The molecular foundation for 14,000 miles of steel cable forms right inside the heart of the factory. An electric arc furnace rises to the height of a 5-story building. Massive graphite electrodes descend into the chamber. A blinding flash of electrical current violently strikes the mixture of purified iron ore and high-grade scrap. The solid mass collapses. It transforms into a blinding, viscous fluid at over 1,600 degrees Celsius, flowing like thick volcanic lava. The radiant heat instantly warps the air, forcing engineers behind heavy thermal glass. This is not simple melting, it is surgical chemical synthesis. Metallurgists actively program the mechanical properties of the steel by altering its exact atomic structure. Manganese drops into the crucible to maximize extreme hardness and wear resistance. Chromium and nickel provide critical immunity against environmental corrosion, while silicon alters the matrix to increase overall ductility. The final metal must stretch under hurricane stress without breaking. Absolute molecular control. During the fusion phase, automated silos dump quicklime and fluorite directly into the boiling bath. The compounds trigger a rapid reaction, generating a thick layer of slag on the glowing surface. This floating crust acts as an aggressive chemical sponge. It physically extracts structural poisons like phosphorus and sulfur from the molten iron matrix. Once chemically perfected, the liquid steel drops into a continuous casting line, plunging rapidly through water-cooled copper molds. The perimeter freezes instantly. The core remains dangerously hot. Industrial torches slice the continuous glowing extrusion into precise square billets. Casting these heavy solid blocks permanently locks in the perfect chemical alloy. But this is merely a raw blank before the main physical trial. To continuously feed the 1,600-degree inferno of the arc furnaces, mining crews must dismantle entire mountains day after day. The origin of an elegant suspension bridge cable lies far from the sterile precision of the steel mill, rooted deep within the brutal expanse of open-pit iron mines. Industrial titans battle solid earth. Heavy drill rigs bore deep into the bedrock to create precise geometric grids of blast holes. Blasters pack these cavities with chemical agents, heavily relying on industrial explosives like ammonium nitrate mixed with fuel oil. A perfectly timed electrical sequence triggers the charge. The mountain shatters. A shockwave rips through the quarry, releasing thousands of tons of iron-rich red rock. Hydraulic excavators emerge through the settling dust. Their steel buckets match the exact dimensions of a standard living room. With a single mechanical sweep, the excavators gouge the fractured earth and dump the heavy ore into waiting haul trucks. These massive vehicles carry payloads of 400 tons per trip. That equals the weight of 2 empty Boeing jumbo jets moving down a dirt road. The dull roar of high-displacement diesel engines fills the canyon. At the staging areas, the ground vibrates violently under the sheer mechanical force of preliminary processing. Massive vibrating screens aggressively filter the crushed boulders by physical size. High-intensity magnetic drum separators then sweep over the moving conveyor belts, instantly pulling the iron fragments upward while stripping away useless clay and sand. The separation is rapid and absolute. This raw concentrate now begins its transcontinental journey. An endless chain of heavy-haul freight trains and maritime bulk carriers continuously moves these fragmented mountains of ore toward the smelting plants, closing the massive logistical loop. The chaotic mountains of extracted ore have been purged and cast into flawless steel billets. Now, these dense monoliths face 1,000-ton mechanical profiling. Still radiating a pulsating orange glow, the metal enters the primary rolling mills at over 1,000 degrees Celsius. At this extreme heat, steel surrenders its rigid nature. It behaves like heavy, pliable dough. The blocks feed into a synchronized sequence of high-strength alloy rollers. The machinery strikes with devastating force. Thousands of tons of pressure crush down on every single millimeter of the red-hot block. The physical load is massive. It equals the weight of 3 fully loaded freight cars balancing on a surface the size of a coin. This mechanical violence is not merely about altering exterior dimensions, it rewrites the internal physics of the material. Under extreme compression, the crystal lattice of the metal undergoes dynamic recrystallization. Microscopic internal voids collapse entirely. The chaotic grain structure realigns into a tightly packed unidirectional matrix, multiplying the structural density of the steel. With each rapid pass, the thick billet stretches and thins. It transforms from a coarse slab into a continuous flexible line of wire rod. Cooling happens under absolute environmental control. Any sudden drop in ambient heat would instantly induce fatal microscopic fractures across the newly forged surface. A strict diameter of precisely 6 millimeters and a core temperature of 900 degrees are permanently locked in, a single second before the rod transitions into the high-speed micro-drawing dies. No ultra-high-strength steel will survive even a couple of years in a marine climate if it is not clad in a chemical shell. This is survival factor number 1. How do you force a metal to willingly destroy itself to save a megastructure? The answer lies in an electrochemical paradox. Before the transformation begins, the raw wire passes through a bath of mild acids, stripping away every microscopic impurity and residual lubricant. Clean steel meets extreme heat. The stripped thread plunges directly into a vat of boiling liquid zinc. The blinding glow of the molten metal bath illuminates the factory floor. 450 degrees Celsius. At this precise thermal threshold, a violent atomic exchange occurs. Zinc does not merely wrap around the steel, it actively alloys with the surface, forging a permanent metallic bond. This newly fused barrier acts as a microscopic chemical spacesuit for thousands of tons of heavy steel. The physics of the sacrificial anode dictate a strict hierarchy of decay. Because zinc possesses a higher electrochemical potential than iron, it actively draws the destructive forces of nature toward itself. If a deep scratch breaches the coating, corrosive moisture attacks the outer layer first. The zinc literally bleeds electrons to protect the core. It corrodes completely, dissolving over decades to shield the structural steel beneath. One metal dies, the other lives. For extreme coastal environments, engineers seal this metallic union under secondary barriers of epoxy polymers or microcrystalline wax. But chemical theory requires immediate physical proof. The newly armored wire enters the testing grips. The thread is aggressively twisted into tight knots by relentless machinery, proving the absolute indestructibility of the coating before transitioning to the core analysis. Beneath the 450-degree zinc shield lies survival factor number 2, the mechanical density of the core. Paradoxically, this ultimate strength is forged not in a roaring furnace, but at room temperature. High-pressure water curtains instantly strip away the residual heat of the initial rolling stage. The molecular structure stabilizes, the real transformation begins in the cold drawing line. Massive winches aggressively pull the steel wire through a succession of tungsten carbide dies. This material ranks at 9 on the Mohs hardness scale, sitting just beneath diamond. The friction is absolute. Colossal mechanical tension forces the metal through microscopically shrinking holes. Solid high-tech lubricants coat the surface, preventing the wire from tearing itself apart under the immense shear forces. The machinery deforms the metal at room temperature. This triggers a counterintuitive physical law known as strain hardening. By forcibly compressing the crystal lattice, the process causes structural dislocations inside the iron matrix to pile up and physically lock together. The narrower the wire gets, the harder it fights back. Forced thinning mathematically multiplies its tensile strength to extreme limits. The thread flies through the drawing blocks at speeds reaching 30 meters per second. Red laser beams cut through the mechanical haze. These optical sensors continuously scan the thickness of the flying line in real time. The operation demands absolute perfection. The allowed margin is 0.001 millimeters. That is a deviation 50 times thinner than a single human hair. It is a microscopic constraint designed to dictate the survival of a macrostructure holding thousands of tons of suspended concrete and steel. Automated traction systems instantly correct any irregularity detected by the lasers. The monitoring arrays lock the final diameter with a strict tolerance of exactly 1/1000th of a millimeter, permanently sealing the physical geometry of the metal. But neither the chemical shield nor the micron-level density from cold drawing will save the cable from snapping if its atoms do not pass the third factor. They need a complete thermal reboot at 900 degrees Celsius. Engineers apply extreme heat here, but they have no intention of melting the metal. The furnace acts as a chamber for reprogramming the carbon hidden inside the iron. Metallurgists are hunting for a structural paradox. They must forge the perfect balance between diamond-like hardness and spring-like elasticity deep within the crystal lattice. The steel wire steadily feeds into a controlled atmosphere, quietly absorbing thermal energy until it reaches the critical threshold. At exactly 900 degrees, the internal geometry of the metal shifts. The steel opens up into its austenitic phase. Carbon atoms break free from their rigid historical patterns, migrating through the expanding iron network to distribute themselves with absolute uniformity. This slow, methodical climb to peak temperature sets the stage, but the actual transformation requires brutal contrast. The glowing thread leaves the gentle heat of the furnace and plunges instantly into a rapid cooling zone filled with liquid molten salts or industrial oils, a violent thermal shock. This sudden drop in temperature traps the carbon atoms before they can revert to a brittle formation. The liquid forces the atomic architecture to snap into a tightly woven structure known as fine pearlite. This dense internal geometry gives the steel remarkable flexibility to handle immense dynamic loads without stretching out of shape. The atoms freeze in a perfect pearlitic matrix, leaving the thread in a state of kinetic tension before the final macro assembly. The chemical shielding from the previous stage is just preparation. The true ultimate strength of a mega cable reveals itself only through intentional destruction inside an armored chamber. How exactly do engineers ensure the cable withstands such colossal loads before snapping? The answer requires uncompromising physical sacrifice. Every finished batch carries a flawless digital passport. Software guarantees full traceability, tracking the structural history from the original iron ore mine down to the exact temperature of the final galvanizing bath. Heavy cranes load the finished wooden spools onto transport ships, but data and swift logistics cannot support a suspension bridge. The steel must physically break to prove its integrity. This is an extremely expensive necessity. A single high-end cable commands a market value comparable to a luxury sports car, costing anywhere from 50,000 to 200,000 euros. Sacrificing one means destroying premium capital to guarantee survival. Technicians lock a thick test section inside the heavy steel walls of the bunker. The colossal hydraulic traction machine engages. The massive mechanical rams pull. Tension escalates rapidly. The steel fibers stretch, fighting the immense force. The air vibrates. Hydraulics tear the test sample apart with a deafening crack of rupturing metal in the confined chamber, cutting the scene at peak tension and throwing us back to the assembly process. To ensure a test specimen withstands colossal loads, engineers rely on more than just the sheer thickness of the raw steel. They depend entirely on the precise geometry of mechanical braiding. The operation unfolds inside planetary stranding machines. These colossal rotary structures, towering like three-story buildings, hold hundreds of massive steel spools simultaneously. When engaged, they spin into a deafening mechanical cyclone. The machine revolves rhythmically around a central core, drawing individual steel wires under relentless stress. It weaves them into a strict helical pattern. This spiral configuration dictates the ultimate survival of the material. It operates precisely like a woven finger trap. When immense weight stretches the main cable, the angled strands inherently constrict against each other. Tension generates compression. The harder the load pulls down, the higher the internal friction rises, locking the independent threads into one unyielding solid mass. The architecture builds outward in three distinct concentric zones. The inner ring grips and stabilizes the core. The intermediate layer absorbs the primary structural load. The outer shell serves as sacrificial armor, engineered specifically to deflect severe physical abrasion. Precision rules the entire sequence. Automated computer systems strictly regulate the drawing tension to prevent the formation of a single microscopic air gap. But even a perfect computer assembly leaves microscopic voids. Without special treatment, these gaps will become an incubator for hidden corrosion. Condensation acts as the silent executioner of megastructures. The braided monolith passes through a high-pressure injector ring. Heat radiates from the massive steel nozzles. A viscous, gleaming wave of hot synthetic lubricant blasts into the cold metal matrix. The mechanical pressure forces the thick liquid deep into the core. It penetrates so thoroughly that it floods empty spaces thinner than a human hair. Total saturation. This is not a standard industrial oil. Engineers utilize advanced thixotropic compounds. At rest, the substance behaves as a dense, immovable gel. But under physical stress or sudden pressure changes, its molecular structure shifts. It drops in viscosity and flows completely freely, rushing instantly to seal any newly formed microcrack. Outside, the cable presents a hard, rigid steel shell. Inside, it harbors a fluid, active chemical environment. The wire rope transforms from a static piece of iron into a dynamic system equipped with liquid armor. When heavy winds strike, a suspension bridge naturally oscillates. Millions of tightly wound steel filaments rub against each other with crushing force. The thixotropic compound acts exactly like synovial fluid in a human joint. It drastically reduces internal friction. The steel strands glide instead of grinding. Zero internal wear. The rapid cooling sequence locks the chemical barrier tight. The fully sealed tendon emerges from the production line, engineered to withstand aggressive environmental onslaughts for over 8 decades without surrendering a single pound of its original load-bearing strength. The finished, hermetically sealed, and tested monolith leaves the walls of the Megafactory to become the steel tendon for the infrastructure of the future. This journey starts in absolute chaos. The deafening roar of the electric arc furnace annihilates raw scrap metal at 1,600 degrees Celsius, a temperature hot enough to effortlessly liquefy solid rock. Pure thermal violence. Months later, that exact metal exists in the calculated silence of a finished suspension bridge. To accurately map this metamorphosis from a chaotic liquid bath into a high-tech engineering masterpiece, artificial intelligence and high-precision simulations track the microscopic thermal reactions inside the steel matrix. Human vision fails here. Only digital modeling reveals the hidden dynamics that give the final cable its relentless strength. These massive cables serve as the invisible supports of modern megacities. They hold the physical weight of global trade and daily commutes, silently resisting decades of gravitational pull and wind fatigue. If decoding this precise transformation of raw iron into the backbone of human progress brings value, supporting with a like and a subscription directly fuels our next expedition into the extremes of industrial engineering. Thousands of vehicles cross these colossal spans every single hour, trusting a quiet web of highly tensioned wire. But behind that engineered silence, what is the true cost and microscopic complexity of the steel suspending our world above the abyss?